Hi, my name's Joel Luke and I'm a PhD student in the Nanoanalysis group at Imperial College London, and today I'm going to talk about a new publication that we've done in collaboration with CSEM Brazil, and it's about the use of organic photovoltaics for low light applications. If we look at the big picture, what we're trying to do is contribute to the solving the energy crisis by looking at green energy production technologies. More particularly, what I'm interested in is using organic photovoltaics, which are solar cells that are made out of a mixture of polymers and small molecules, and then we use these to produce electricity. So our organic photovoltaics have some really great properties that make them really good candidates for low light applications. These being flexibility, low weight and tunability, so you can change the colour. And all of these things mean that you can easily integrate them into devices in our homes or into the architecture itself. It also means that we don't need to use mains power or batteries, which cause a lot of waste. And so what we wanted to do was look at some of the current materials in our field, those that are stable, easily scalable, and reasonably efficient, and to look at the applicability of those for these low light applications. So we concentrated on the P3HT OID-TBR photoactive layer, which is a really good blend as it shows really good stability and reasonable efficiency and has already shown scale-up potential. And so we integrate this into a device architecture that's easily scalable with all the layers being printed, which is different from the literature. And the first thing we do is compare it to silicon solar cells at low light and demonstrate that the organic solar cells are much better at low light, which is really great. The second thing we do is then we look at optimization techniques to try and make our solar cells as efficient as possible. And we look at a few different techniques and a few different relationships to work out how we can optimize our devices. And this is quite different to the device optimization for solar irradiation, so for outdoor solar cells. Thirdly, one thing we noticed when we were measuring our solar cells at low light is that there's this really big light soaking effect. So to get really good performance, you need to light soak your device under one sun, which is really high light intensity, or for quite a long time. And this is really bad because you need stable and high performance if you want to use it in a commercial application. And so we investigated the origin of this light soaking effect, and it was found that the interface between the photoactive layer and the electron transport layer, which was zinc oxide, was not great. And zinc oxide itself has a lot of mid-gap states which affect the electron transport of the zinc oxide and affect the electron extraction at this photoactive layer and electron transport layer interface. So what we did was then, after finding out that zinc oxide was the culprit, we replaced it with some tin oxide nanoparticles, and these showed no light soaking effect because there aren't many trap states and the energetics at the interface were much more stable. And then the last thing we did was we used this light soaking free device architecture to produce a scalable module and demonstrated that the performance of the module is still really good and still gives an option for commercialization. So I think my favourite figure has to be the last figure, because it's here that we really demonstrate the applicability of our solar cell for a scalable low light module. And it also highlights a couple of the other conclusions from the paper. So the first one being that the zinc oxide has this light soaking effect and the tin oxide doesn't, and also that the one sun performance of the modules isn't indicative of the low light performance. And so in all, it is showing the scalable potential for commercialization of these organic photovoltaics. So the take-home messages are first and foremost that organic photovoltaics are a really good option for low light applications. Secondly, that when we're making these modules, we need to think about optimization for low light and not just use one sun solar cells at low light, because we've shown that that isn't a good approach. And then thirdly, that we should pay really close attention to the interfacial energetics for low light, because this light soaking effect is really critical for low light performance, and so you have to use interlayers and photoactive layers that minimise this as much as possible to get the most out of your solar cells at low light. So there are a few questions left to answer and a few questions that come up from the paper, and these relate to the light soaking effect and zinc oxide. So one thing to do would be to do a more systematic study of the energetics between the photoactive layer and the zinc oxide, and this might help us to understand the light soaking effect better. One thing related to this is to look at the zinc oxide itself, and can we control the number of trap states, these mid-gap states, or if we can change the energetics of the zinc oxide, and so we could use nanoparticles or we could use passivation as an approach to that. One thing we didn't touch on was the stability at low light, but we really don't think this is going to be such a problem at this lower light intensity compared to organic solar cells for use outdoors. And where the research really needs to go is to look at the more high performance materials in our field. So in the literature there's some materials with really high efficiencies, but are they scalable enough? Are they stable enough? And that's really where the work needs to go. And I guess the big question is, will organic solar cells break into the energy market?